only 5 minutes, linear quadratic irregularities. Then we will go to the next topic. Is it okay? So what I discussed yesterday is that, which I want that all our academic staff should tell to the students, that nothing exists, it starts. Because unless you know that thing, your understanding of the poles, zeros and system concept will not be clear at all. So everything is energy and we all are vibrating at different frequencies, right? That is clear, that must be very clear. That we are all vibrating bundles of energy at different frequencies. And we have got several characteristic modes. We vibrate at different frequencies having many characteristic modes. And those are the poles of the system or the eigenvalues of the system. And they are also called the singularities of the system. They are system singularities. And second point is, we have also got some zeros. That is the frequency which will not respond. Okay, we will block that frequency. As I gave you some analogy, that you are not supposed to answer all questions. Certain questions you will not answer. So that is the zeros of the system. Then we talk about static systems, dynamic systems. Dynamic systems has got at least one energy storing element. Because of the memory, there is a possibility of instability, right? That's the. Next, we say that there is no need of designing any controller. If the open loop performance is satisfactory, that's fine. There is no need. We are happy with that. But usually the open loop system is not satisfactory. So we have to design the controller. But we have to design the controller provided the system is controllable. If the system is not controllable, there is no point that we should design the controller. That point I discussed. But what is not emphasized in the textbook is controllability, that particular property of the, that is not the property of the system itself. This is the property of the system matrix as well as the input matrix. That means, as I told you, the same system can be controlled by changing the input signal, right? B matrix. That is very important. So if the system is not controllable, you have to make it controllable if possible. And if you cannot make it, don't waste your time. That is just mere waste of time because the system will not respond, right? There is an important theorem, the pole placement theorem, that says if the system is controllable, condition number 1, then it is possible to place the eigenvalues anywhere in the S-plane by an unconstrained control signal and using state feedback. So there are 3 conditions now. The system must be controllable. The feedback mechanism is not output feedback mechanism, it is a state feedback. Output feedback may not possible place the poles anywhere. So first the system must be controllable. You must use not output feedback but state feedback. And you should not constrain the control input. Control input should be unconstrained, right? With constrained control input, you cannot place anywhere in the S-plane, right? But there is a catch. The catch is, we assume that because you are using the states as the feedback, we assume that the states are measurable. Or we can access the states, right? If we cannot access the states, then you have to estimate it. We will talk about the estimation today in a different topic. We have to estimate it. How to estimate it? We have to estimate it by using a formula from the output measurements and using an algorithm with a formula that is called the observer. Observer is essentially a mathematical expression. So by using the observer, you can estimate the states, and instead of the actual states, you put the estimated state. I am just writing here. U is equal to minus kx earlier. Now this u will be equal to minus k x cap. So this x is now replaced by x cap, and this x cap is obtained from an observer. Now the point is differential. Observer can estimate the states if the data is not corrupted by noise. That point is not emphasized here. If the data is not corrupted by noise, then we can estimate the state of the system from output measurements by an observer. But if the data is corrupted by noise, you can estimate the state not by an observer but by a Kalman filter. Kalman filter does the same thing. It estimates the states. Kalman filter is essentially estimator, right? But if noise is there, then you have to use a Kalman filter. So what is the difference between the Kalman filter and observer? They both estimate the states. One works when the noise is not there, another will work when noise is there, right? Now say this, and that particular estimator, it has got a name that is called a linear quadratic estimator, Kalman filter. Linear quadratic estimator, LQE. In the MATLAB, there is a command called LQE. This command will estimate the states. You give the noise statistics. Okay? You give the noise statistics. LQE, linear quadratic estimator, essentially a Kalman filter. Okay? So it will estimate the states. Now you can ask him, why not an observer? Observer is fine. If there is noise, observer will not work. Kalman filter also will not work. You see, it is linear quadratic estimator. It is linear, it is quadratic, and it is an estimator. What is the linear? What we are talking LQE, it is only applicable for linear systems. Kalman filter can be designed for nonlinear system, that is a different issue. But linear quadratic regulator is only for linear systems. It assumes the performance index is quadratic and is an estimator. So therefore linear quadratic estimator. Now comes noise, because when there is noise, we have to estimate the states by using estimator, Kalman filter. Noise is the problematic things. We will talk about these things today itself in the other aspect. I will just give an example here. See here, a plus b whole square. Let us see. Very fundamental. A square plus 2ab plus b square. Everybody knows it, right? This is an identity, this is not an equation. Okay, this is an algebraic identity, this is not an equation. Okay. How can you compute a plus b whole square? You see, this is a very simple thing, but it gives you a very clear message. Just wait for now. A plus b whole square, you can compute provided you know precisely what is the value of A. You know precisely what is the value of B. Then only you can calculate A plus b whole square, right? That means if A is a deterministic variable, B is a deterministic variable, then only you can find out A plus b whole square. If A is a random variable and B is a random variable, even A plus b whole square you cannot do it. Suppose I will say you the temperature of this particular room is a random variable. The temperature of the next room is also a random variable. You cannot do the addition of the temperature of this room and the temperature of that room. You cannot add it because you don't know its value precisely. Because you don't know its value precisely. You understand this point? A random variable by definition whose value is not precisely known. And if you do not know the value, how can you compute? You got a point? So, with tricky things. So, what we will do, if the variable is a stochastic variable, a random variable, you convert the random variable to a deterministic variable. Not a merely a deterministic variable, but I am telling from that understanding concept. Convert it to a deterministic. Then you apply the deterministic formula. Because this formula is for deterministic variables, right? Now what is that? The temperature of this particular room is a random variable. Because you do not know what is its value precisely, right? But over the day, if you measure the temperature at each time and find out the mean value of the temperature of this room is a deterministic variable. You got my point? The temperature is random, but if you take the mean, it is not random, it becomes deterministic. So now you can a plus b whole square instead of a plus b whole square, you see, you can instead of T1 plus T2 temperature whole square, you cannot compute. I am writing like this, you cannot compute. But T1 bar plus T2 bar whole square, you can compute. Because T1 is a random variable, T2 is a random variable. But T1 bar and T2 bar is not a random variable, they are deterministic. Right? So we are applying mean value of the probability operator, or any type of many sorts of operators are there. So that converts this stochastic variable to a deterministic phenomenon, right? So linear quadratic estimator, it will estimate the states when the data is corrupted by noise, and noise should have the Gaussian statistics. Noise can vary, you see the statistics should vary in the Gaussian pattern, non-Gaussian pattern, there are different types of probabilities there, okay? So if you are estimating the states using the Kalman filter, okay, then another thing I will tell you, linear quadratic estimator. In engineering and science, we have got mainly two problems. One problem is called the regulation problem, another is called the tracking problem. Regulation problem means we want, say for example, the power system. We want, no matter how the disturbance is there in the system, the frequency deviation should be 0. That is, the frequency should be maintained at 50 cycles. The deviation in frequency should be 0. This is a regulation problem. The frequency should be regulated to 0 under disturbance. Clear? This is a regulation problem. What is the tracking problem? Tracking problem is different. The speed of the DC motor should be this 1500 minus 1500 plus 1500 like this. You got my point? Tracking problem, you see here. See, this speed, right? Tracking problem, or else tracking problem, radar tracking problem, it is tracking, right? Robot path planning is a tracking problem, it is not a regulation problem. You track it, right? You track it. In the pole placement type controller which I discussed yesterday, it is a very powerful controller because you can place the poles anywhere in the S-plane by unconstrained control signal, right? But the problem is where to place the poles. Where to place the poles, right? So to avoid that, a new theory came up linear quadratic regulator. Instead of placing the poles, you optimize one performance index. You optimize one performance index, usually the performance index is like this. You optimize a performance index, okay, X transpose QX plus U transpose RU, okay, and find out the same control law, U is equal to minus KX. So this problem is called a linear quadratic regulator. The name is, this is applicable for linear system. The performance index which you are minimizing is a quadratic performance index, and you are solving a regulation problem, right? Not a tracking problem, not a tracking problem. So therefore, this is a linear quadratic regulator. It is essentially a state feedback controller. And in the MATLAB you will find LQR. You give a command like LQR, it will give you the K. K is equal to LQR, and there is something, you see. All the matrices you can give it, you can get it. But in pole placement you give K is equal to place or occur, ABP. You see same K, but you will get different value of K, but this is the K, the state feedback again, LQR and place, linear quadratic regulator. So linear quadratic regulator essentially is a regulator, and it optimizes a quadratic performance index and is applicable to linear systems. Therefore name, right? Now same thing, state feedback. If the states are not measurable, you have to put an estimator. Linear quadratic regulator can also be used with an observer, no problem. But usually data is corrupted by noise, so you have to estimate by a linear quadratic estimator, right? So linear quadratic regulator plus the estimator LQE is give you linear quadratic Gaussian controller. We say observer based controller. Observer will estimate the state feedback combined together, observer based controller. Exactly same thing, linear quadratic regulator. It is not placing the poles. What it does? It optimizes the performance index. Linear quadratic estimator, it estimates the states, combine them together. It is linear quadratic Gaussian controller, right? Why Gaussian? Because we assume that the noise follows a Gaussian distribution. Okay? And why linear? Because it is applicable to linear system. And quadratic because the performance index is quadratic. Got my point? So linear quadratic regulator plus linear quadratic estimator is equal to linear quadratic Gaussian. Now, if you want that it should track something, you have to put an integrator. Yesterday I told you the integrator can do all these things, steady state. Those things are always there. Okay, but this is point. So, I will close these things now. Now we will go to the next one. This is lecture 3, na? Modeling. Bigger? Full screen mode. Is it there or not? No? Earlier it was full screen. Is it there? No? Huh? Oh, start. Oh dear. You are intelligent. People in the area of all engineering and science, they always say, we are genius, we are intelligent, we can do everything. But only the thing, you do one thing, you give us a model. Given the model, they can do everything. Everyone, you see, 99% people, more than that, given the model, they can analyze the system, they can design controllers, they can do all sort of things, right? But who will give you the model? Who will give you the model? If you give model is given, that's fine, easy, right? So the question is, we will discuss all this in detail, and today also in the tutorial you will do it by yourself, and that will be easy, not like yesterday's things which you could not do it, you will do it. People will say, give us a model. Give us a model, then we'll do it. The problem is, if I want to go to the market to purchase the vegetables from a house or from the, I'm living in the campus, and there's a vegetable shop outside. If I want to go to there, a simple bicycle will do the job, right? Simple bicycle will do the job. If I want to go to the beach to have a view, I can take my car. If I want to go to Bombay, I need either a train or plane, right? And if you want to go to super space, then you require something different, right? So the question is, in your house, everything is there. You have got a bike, you have got a bicycle, you have got a car, okay, you have got money to buy the plane tickets also. The question is, which one you will take? So taking a plane to go to the vegetable shop is not foolishness, it's a bloody foolishness. You got my point? You may think it is easier to know. I'm telling you, this is the most difficult part. I've got a student, I remember he was a mechanical engineer, and he did a PhD. I was the course supervisor, Oliver Grant. One day Oliver came to me and said, Dr. Swain, I will work on chaotic systems. We'll discuss those things later on in nonlinear system. I told Oliver, your problem is designing controller for the helicopters and all these things. You start from the LQR, LQG, and then proceed further. No. Can I identify, he told, can I identify a helicopter model? I told, why you want to identify a helicopter model? Why? No, I do not know, because I knew that you have worked with a very big source. From the Google Scholar I found out, so I thought, let us do some modeling. I told, you see, you must first decide what you are going to do, why you want to do it. Because doing is not a fun. It requires lots of mathematical knowledge and so many other things. We will see that. So taking it, whether you will take a bicycle, plane, or a bus or a train, that decision is extremely difficult. As you have lecture proceed, you will know it, right? So similarly, fitting models, how to fit the models, we will discuss later today. But which type of models? Models are many. There are so many types of models. Let's see. Modeling is given a set of input of data, find a mathematical model. Okay, see. First, let me go to this slide, and then we'll see. In the modeling, what you do, I will come back to that point. I have got a system, and I have to fit a model. So I will apply the same input to the system, same input to the model. So I will get an error, then I will use this error to update the model, right? Very standard system identification, right? Things are not that easy. And I am telling you in this lecture and coming lectures, I will tell certain controversial things, okay, which many people think that is wrong, and we think that is right, 100% right. And we have got the authority to tell that thing, because we have published papers on that, and we have worked in the big shots in the world. We will say, and the people have to follow. There is no other way out. We will see that, right? This diagram looks very simple. I want to mimic the system behavior. The model has to mimic the system behavior. You apply the same input to the model system, same input to the model, you get the error and update the model. This is the standard thing. Which model? Models are many. Let us see. Let me give an example. You see, I am here. I have got many models. See, first model. I am the son of my father. One model. Second model. I am the father of my son. Clear? Third model. I am the teacher of my student. Fourth model. Otherwise, right? So many different types of models. Which model you should use? Extremely difficult decision. Which model you will use? Which model you will use? Right? There is a saying, a person with one watch is sure what time it is. A person with multiple watches is never sure. Because no watch will give the same timing. There will be at least some precision wise, there is some error, right? If there is, see, you will find, if you are getting one job, then you go and join. In a campus, if a student is intelligent, he gets multiple places offer. One from Google, another from Microsoft, another is from Accenture. Then he is problematic. Which one he will take? If you have got a point? So models are many. Which model you will use? Various types of models you see here. There are many types of models. Parametric models, non-parametric, continuous, discrete, long, distributed, deterministic, stochastic, linear. Oh dear. See, too many choices. Man with one watch is sure what time it is. Man with multiple choices is not sure. Right? Which type of model to be fitted to the data? Which factors will determine that which model to fit? That is a difficult decision. Okay? Yeah, difficult decision. Okay. There are different types of models we'll discuss today, and we'll also see the and second thing is, why you are going to fit the model? As I told you yesterday, it is not an intellectual form, it is not an intellectual gymnastics. Because Minister of Energy, Minister of Human Resources is giving some money, and there is a GIAN course is conducted by two professors from your own department, and a person coming, idiot fellow coming from outside, Government of India is giving money. It's not a bloody form. What a point? That was to goal. Why you are doing it? As the student told, Dr. Swami, I want to fit a model. Why the hell you will fit a model? No, I don't know. You don't know why to fit the model. Then go away. What about models? Whether you will use it for prediction purpose, we'll discuss those things. Prediction problem, control problem. Whether you will use it for control purpose, whether you will use it for analysis purpose or verification. What is the purpose? First you decide. Why I am telling these things? Because you are academics. Whenever some students come here, I am telling you one thing. I have got around 25, 30 students, PhD students I have supervised. Problem is not by solving the problem. People are intelligent, they can solve the problem. The problem is finding the problem, formulating the problem. That is important, not the solution. Solution is easy. A man in the street I can bring him from the Queen Street, he can solve the problem. I tell to students, I can go and stand in the Queen Street, ask the people, come and solve it. They will come. Got a point? Problem. Okay. So you must be very careful about that. Extremely important thing. I will discuss these things later on because I have given an example here. One day one of my friends, we are colleagues in the Aris Raulkala. He is now UNSW, Australia. So he came for a PhD examination and he was talking that we have got a manufacturing problem. Okay, I am not discussing those things. So they have got a fiber, they have to manufacture. So there are 20, 30 variables, input variables, and there are output variables. So they do not know how these input variables affects the output variables. So we are discussing on the launch table. I told you, see, what you are talking about, he is a mechanical engineer. It is not a control problem. It is a prediction problem. It is not a control problem. It is a prediction problem. So the prediction problem, and there is no need of any interpretation also. So a neural network can do the job. Neural network is very good for prediction. Neural network is very good for prediction. Completely useless for interpretation. You cannot interpret anything from the weights of the neural network. Okay? I told this is the prediction problem, and neural network can do very good for prediction. Give it. And I have got a student from Sri Lanka. He is now in the German aerospace in Chatura. I told Chatura, you do it, and Chatura did it. And we published a couple of papers in the transactions. So we have to identify what is the prediction problem, which type of problem it is, right? So model building begins with an objective. Assumption. You see, all these wordings I am telling you are very careful. Precisely, model building begins with an objective, with an assumption, and a prior information. And second line is, be aware of the assumptions and beware of the assumptions. You must be aware that what assumptions you have taken, and you must be very careful what assumptions you have taken. Okay? Suppose you are assuming the noise is Gaussian, but actual noise is not Gaussian. It is something different. So you will not get the result. What a point? So you must be aware of the assumptions and also be very careful about the assumptions. So first thing, why you are fitting a model, not a phone. Which type of model you will fit it, right? There are many types of models. That also you have to decide. And once those things are there, other things become straightforward. In this particular course, because we are going to study minimum variance controller and subsequent adaptive controller, if you want to design a minimum variance controller, we will discuss those things, not today, tomorrow or something like that. If you want to, I am telling you, if you want to design a state feedback controller, the system must be modeled by a state space model. If you want to design one H infinity or robust controller, system must be in state space. If you want to design a generalized predictive controller, system must be a discrete parametric model, which we are talking about. Okay. If you want to design a feedback linearizing controller for nonlinear system, system should be in a different format. First you get a model in that particular format and do it. You got a point? I am just giving an analogy here. The same person is same. I want that he should act as a king. So which type of robes he should wear? Should he wear this type of shirt with the half sleeves? The king will have nice dress, velvet dress, right? The same person will act as a beggar. Should you give him a velvet dress? You have to give a different dress. Got a point? So similar thing. The system may be same. What do you want to do with the model? Accordingly, you will get it. Got a point? So that is a very crucial point. If a person is doing the beggar role in the drama, and you put a velvet dress and with a head, crown, how it will look? It will look bad, right? Remember, I can talk many things, but I don't want to divert. You see, because my father-in-law is a professor in the literature, so I read quite a lot of literature. I read a lot. I'm a voracious reader. A drama is good. A theater is good. When you go to see a movie, okay, there are around thousands of people are watching, or here in India, lakhs of people are watching, okay? Everybody is saying the movie is good. The movie has got 50 characters. Somebody will say, that heroine, she is so beautiful and glamorous. Then others say, forget about that heroine, she is bloody useless. Have you seen the acting of Amir Khan? He is nice. Then another fellow will tell, what does the hero is doing? See the villain, ominously is villain, so villainous dialogue you can see. Then somebody will say, all is nonsense. See the comedian, Johnny Lever, how he is acting. Now see, the picture is successful. You see, the audience is different characteristic. One is liking the hero, another is liking the heroine, another is liking the villain, another is liking these things, right? A picture is successful not because the hero is acting well, or the heroine is glamorous, or the villain is doing his duty properly. It is because everyone is doing their duty properly as intended by the director. Got my point? What the director intends, if the comedian will not do the comedy, the entire show will flop. Got my point? So this is what exactly these things. When you are doing certain things, you are designing a minimum variance controller and using a state space model, it will not work. It will not, just like putting a very nice robe and doing the job of a beggar. It will not work. Got my point? So you must be very careful. We will discuss today this particular hour parametric models, because we will use this model for my design. Okay? Discrete parametric model. It is discrete domain and parametric models. The structure of this thing, I am just going very quickly, we can go. You see here, the main difference here is, it has got a noise model and it has got a process model. The system, the data is corrupted by noise, you are measuring the data and the data is corrupted by noise, right? So you want to fit it, right? So this model, what happens? There is a noise model and there is a process model, right? What a noise model will do, not exactly true, it will capture the noise dynamics. Now noise doesn't have any dynamics, but I am telling in the sense, it will capture the noise part and the process model will capture the dynamics of the system. Say, for example, I am giving the analogy here. In the classroom, not only the academic staff, there are some bloody idiots coming from outside as well. Right? So what I will do now, I have my own mechanism, I am fitting the model. I will catch the way the academic staff will be separated and those people who are useless, they will be separated by a, right? Because my people are there, they can easily detect who are the useless people. That's the mechanism. So the system has got two models, one the process part and the noise part. The process part will capture the system physics. Noise part will do these things, standard model.
These ABCDs are not
Yeah? Yeah. Yeah, that is different than state space. That's very important. This is not a state space model, this is a parametric model, just like a transfer function model. It is not, remember, yes, the Professor Amalkar has told rightly, remember this is not a state space model, this is a discrete parametric model. Okay, this is the structure. Because I usually use it for a minimum variance controller. Okay, minimum variance controller we cannot use state space model. MPC we can use it, but not. Right. The structure of the model here is, you see now first thing here, the usual structure is this D polynomial here, the noise polynomial, the denominator is D, the process denominator is A. Right? Just check it here. So that is the whole difference we will make later on, just a minute. And another thing is, the A polynomial structure, first one is A1, and this is called the monic polynomial. They are called the monic polynomial. Don't enter into so many mathematical terms. And B polynomial in its first term is not 1. First term is B0. Remember, those points are important. Those points are important. You see the definition wise, this is by definition. A polynomial, C polynomial, D polynomial, the first term is 1, 1, 1. B polynomial, the first is not 1. It is some constant, B0. Okay? This is the structure. This is the structure. We'll talk about those things, structures shortly, just don't refer that. Now, there are different types of models. One model is autoregressive model. Autoregressive model, that's a general structure, but not necessarily. There is one model is called autoregressive model. I will explain only these three terms now, carefully. Autoregressive model, yk is equal to 1 by a j minus 1 ek, or yk is equal to, see the point here, yk is equal to minus a1 yk minus 1, yk minus 2, yk minus na. The present value of y is a function of the past values. Clear? This point, autoregressive. Present value of y, yk, is equal to a function of yk minus 1, yk minus 2, yk minus 3. Right? So, regression. Have you heard about the term regression in statistics? Regression, you see, okay, again we have to go to that. Without Indian spirituality, your understanding of engineering knowledge will be a big zero. I don't know whether it is appropriate to tell here because it is getting recorded, but doesn't matter, this is the truth. The entire creation was started. How many of you are doing some meditation? Anybody is doing some meditation? Complete silent. When I say silent means silent. No thought. When I say no thought, no thought. No thought. If you don't have any thought, you yourself, even today also you can find it, you will hear a particular sound. That sound is the vibration of the Hiranyagarbha, is the vibration of the universe, cosmos, Omkar. You will yourself will listen. I am telling you, this is a fact. This is the fact I am telling you. You will listen it. Every day you will listen it. But you have to be completely silent, fully silent. When is silence, no thought, You regress and regress and regress and regress. You go back. Regress means past. Progress means future. Regress and regress and regress. So in the Sanskrit we have got Onkara Bindu Sangyuktang Nityang Dhayanti Yogina. That's the correct thing. So if you regress it, you will find that particular sound where the entire creation has come out. What I point? Regression. You will find, I don't know in Indian television it shows or not. When I was in England, in British Channel 4, there is a program comes hypnotism. There is a person who will come and he will bring a particular person, a live show. He will ask him to sleep and he will say, okay, where are you? Where are you? Where are you? He will say, I am in Ireland, Dublin. Go back, where are you? He will be telling that. He told, yes, I could see a church. There is a tree, no leaves, it's winter. It's snowing now. I'm feeling, he will say, regress. You see, regression. If you regress, go, hypnotism, people do it. So they go it and they find out what is there, right? Similarly, this is the regression. Yk is a regression. Yk minus 1, Yk minus 2, Yk minus 3, Yk minus 4, Yk minus infinity. If you go to that source, you will find out. It is auto-regression. Because you are finding Yk, it is the regression of itself, auto-regression. So this is an auto-regressive model, extensively used in the speech processing. In the speech processing, this type of model is used. Okay? Auto-regressive model where the output is described by its own regression. Clear? Output is described by its own regression and EK is the modeling error. This is one type of model. Second type of model is a moving average model. You see the structure? Where the output is not a regression. It is a regression not of itself. It is a regression of some noise sequence. Ek minus 1, Ek minus 2, Ek minus 3, moving average. That is moving average of the noise. Okay? It's an average, moving average, because Ek minus 1, K minus 2, K minus 3, you are moving in the regression pattern. Then auto-regressive moving average model, you have got an auto-regressive part and you have got a moving average part. ARMA model. So auto-regressive model, moving average model, ARMA model. Another model, different types of models. ARX model. This model is important. ARX model, here you see, this is the standard transfer function model. Be careful here. You see the generalized structure of noise model, C by D. If you see the diagram here, just compare here. This model is diagram here, C by D. The noise model is C by D, but in ARX model, you see the C by D, the C by D is 1 by A. See the point? This is 1 by A. This A and this A, that's same. See the difference, okay? C 1 by A. And this model is the standard transfer function model. Yk is Yk minus 1, auto-regressive part, plus the input part. This is output and this is input. But it is called ARX model. ARX model, you will do today in the tutorial, very simple one-line command. ARX, that X term is coming from statistics, extra input, exogenous input, auto-regressive with the extra input. ARX model, if you see the structure, you will find this A is there, not a D. Another model is Armax model. Armax model, here you see that C term is there, but this A term and A term, they're same. Process model or Armax model. So mainly, see this point I am telling because I will not next lecture but subsequent maybe tomorrow. The output of the system is described by a discrete parametric model. Z to the power minus d, d is the some constant, you see, delay, b by a, uk, just like transfer function, plus c by a, ek, it has got two parts, process part and the noise part, right? This is the model. This model we will use it in designing the adaptive controller, okay. And another important point to remember, the denominator of the process model and the denominator of the noise model, they are same. Another point, very important. This A here and this A, they are same. They are not different. Okay, Armax model. This model will be used to design the adaptive control, which I will discuss tomorrow. But today we have got so many things to discuss, okay. So this is for all these models which I discussed can be described by this form. How it is described, I will explain you now. Say yk is equal to z to the power minus 1 b0 plus b1 z to the power minus 1 by 1 plus a1 z to the power minus 1 plus a2 z to the power minus 2. So this one will be represented as yk is equal to minus a1 yk minus 1 minus a2 yk minus 2 plus b0 uk minus 1 plus b1 uk minus 2. Okay? This model can be represented in a general structure. What is the structure? This point we will start from the next lecture because this is, I will explain these things. Yk is equal to theta 1 p1 k. You see, this k is not equal to, that means a function of k only. Theta 2 p2 k plus theta 3 p3 k plus theta 4 p4 k. If this model is represented like this, that means p1 k is equal to yk minus 1, p2 k is equal to yk minus 2. I am just writing this, theta 1 is equal to minus a1, theta 2 is equal to minus a2. Do you understand these things? The same system, this point please keep in mind, this model can be represented in the form yk is equal to theta 1 p1, theta 2 p2, theta 3 p3. Where you see, if I just map it, this p1k is equal to yk minus 1, p2k is equal to yk minus 2, p3k is equal to uk minus 1, and p4k is equal to uk minus 2. Clear? So all these models which we discussed, this model has got a speciality. They are linear in parameters. They are linear in parameters. Let us discuss a little bit more on this. Linear in parameters. You see, here, example I have given. Yk, Professor Bilakam, just remember that we are going to put that objective questions for the people. It comes to my mind that we will put this type of questions. Yk is equal to theta 1 yk minus 1 plus theta 2 uk minus 1. Okay? 5, 6 examples I am taking now. This is a linear system or non-linear system. This model, linear or non-linear. linear. Theta 1, you understand the parameter and signals. Force is equal to mass into acceleration. Force is a signal, acceleration is a signal, mass is the parameter. Voltage is equal to resistance into current. Voltage is a signal, current is a signal, resistance is a parameter. So yk is equal to theta 1 yk minus 1 plus theta 2 uk minus 1. Yk minus 1 is a signal, uk minus 1 is a signal, theta 1 and theta 2, they are the parameters, right? So here, this system is linear and non-linear. This is linear, right? This is linear, okay. Just I am writing here. This is linear. Is it linear in parameters or non-linear in parameters? Theta 1 is linear, theta 2 is also linear in parameters. LIP I am writing here, in short, linear parameters. Second example is here. Yk is equal to theta 1 yk minus 1 plus theta 1 theta 2 yk minus 2 plus theta 3 uk minus 1 plus theta 3 into theta 4 uk minus 2. Linear system or non-linear system? Linear. System is linear. Yk minus 1, uk minus 1, uk minus 2. System is linear, right? Linear in parameter or non-linear in parameter? Non-linear in parameter because theta 1 is multiplied with theta 2, right? Theta 3 is multiplied with theta 4, right? So it is non-linear in parameter. Clear? Third example. Yk is equal to theta 1 yk minus 1 plus theta 2 y square k minus 2 plus theta 3 uk minus 1 into yk minus 1. This system, linear system or non-linear system? Huh? Non-linear. Linear in parameters or non-linear parameters? Linear in parameters. What about? This is a non-linear system, but linear in parameter. And subsequently other things will come up, right? If the model is represented as a linear in parameters models, if it is linear in parameters, then we can use least squares techniques to estimate the parameters. Clear? This is the point. Neural network, the so-called multilayer perceptron MLP network, which we have studied in 1990s, okay? It is not linear in parameters. MLP network is not linear in parameters. Radial basis function is a linear in parameters models. RBF network, neural network is a linear in parameters. MLP network is not linear in parameters. So we cannot use the estimate the parameters using the linear least squares technique. We have to use the back propagation or other different Gauss-Newton method, Levenberg-Markov methods, all these other methods are there. Okay. So if, understand this point here, if the system is represented in a model which is linear in parameters, then all the least square based methods can be applied to estimate the parameters. Clear? If it is not linear in parameters, then you are in trouble. Right? So that is why we say we ask the question people, why least square technique is not being used here? Why back propagation? Fundamentally, you have to understand fundamentally because there is not linear in parameters. Radial basis function network, RBF network, is linear in parameters. So you can use the standard least squares techniques. Okay. Similarly, just under 5 minutes. Yes, y is equal to theta 1 plus w1 plus phi minus the center and all these things, radial basis function. Okay. Volterra series. This is for linear system. If you want to represent the system in nonlinear systems, there are so many different ways. One is the standard Volterra series. So Volterra series is an extension of the standard linear impulse response function. H1 tau ut minus tau linear system. Then you use higher order kernels. I am not telling that you should know these things. It is a bit complex. Volterra series, but it is linear in parameters. It is linear in parameters. Volterra series is being extensively used for nonlinear system identification. Okay, Volterra series. And there are many other types of system models which are used for representing nonlinear systems. Hammerstein model, Wiener model, sandwich model. Okay, but I want to tell you one thing here. This modeling thing, very few groups in the entire world working on this. Very few groups, okay? Just countable numbers. One group in University of Sheffield where we are working Steve Billings and his group, and subsequently we bifurcated to many places, some people. Hammerstein model and Wiener model is being extensively used in biomedical signal processing. This is being used by very few people. When I was in Canada, I was visiting a person called David Ostick. David Ostick uses it. If you say this Hammerstein Wiener model, people say, go to David Ostick. He will tell. Nobody else. I mean, when I say nobody else is using actually. Hardly you just count how many people are working on this. Okay. Kalman filter, Kalman filter, if you have got the data and you want to filter it, then you have Kalman filter. But the question is, I'll tell you where the modeling comes. Give me a practical example. We have got some data for the renal blood flow in biomedical data. We got it from the Department of Physiology, from the medical school. We wanted to fit a prediction model. So one of my students, he is a master student, he told Dr. Swai, why don't we use a neural network? Then the other person is a doctor. He just laughed during the meeting. He told, what the hell I will do with the neural network? He said, what the hell is not a bad term in foreign countries, very common term. So what the hell I will do with the neural network? Neural network can predict. But I want to know how, suppose a patient is sitting on the operation bed, something is happening, I will see that which parameter of the model I will change it so that it will change its behavior. Neural network completely loses the physical significance, right? Kalman filter, given a set of data, it is a filter. First thing is a filter. It is not a model. We have to be very careful. It's a filter. Given a set of data, you can filter it out, right? And Kalman filter essentially assumes the system is represented by a model. Kalman filter doesn't assume. That is a different story. So Kalman filter can be used to filter out the data which is generated from nonlinear system. But Kalman filter itself is not a model. Kalman filter can do the very interesting jobs. In the image processing, signal processing, it is doing a great job. Give you an example here. V is equal to IR. Do you know the story behind that? V is equal to IR. Ohm's law, everybody knows it, right? When George Simon Ohm found this law, it is such a simple law. Voltage is equal to current to resistance, right? When he found this simple law, you can go and search in the web also. The people in that university, they just ridiculed him. He told, what the hell you are talking? The voltage is applied and current is produced and it is related by such a simple law. How it is possible? So he has to leave the university. 20 years he stayed outside. After 20 years, people realize that actually what he is telling is correct and these things. So we will talk about those things in the structure selection. You see, force is equal to mass into acceleration. There is a mass, you are performing experiment. How do you know the force is related to acceleration or acceleration q or voltage q or displacement square or displacement exponential to the displacement? How do you know that? Now it is there that force is equal to mass into acceleration, you know it. But that term which is important, that is called the structure selection. So that is the most difficult part. So there is a system, there are different terms, which we will discuss those things later on. So Kalman filter essentially assumes, it is not a model, it assumes the system is described a model. But what we are going to say, no assumption. Given a set of input of data, what is that? Which term has to be there? Where acceleration will be there, displacement will be there, which term will be there? Very difficult problem. Very few people are working on the identification, it is extremely difficult problem. Okay, and I will tell you many controversial things. So Hamilton model, Wiener model, they are used for biomedical signal processing. And if you have got some doubt, ask David West. David does it. I was working with him in Canada when he was there. And he works in some place in University of Delft. Few people are working. And we have got lots of ego problem actually. When you go, we are in Singapore conference, one of my friend in Brazil, I just close it before I will have a coffee break. The Leonard Leung is a big shot in Sweden, big shot in system identification. So there's some group, Leonard Leung was delivering keynote speech. There are 500 people there in the Hyatt. So there are some people sitting there other side. Somehow they could know it. I've got another two people from one in Malaysia and one from Singapore. We are all working with Steve Billings. You will be surprised that, you know, Billings people, don't talk to them. Billings people, you see. We are working with Steve Billings. So, Edward told me, hey Swai, you know, there are the bloody bastards, there are living people, they are not living people, they are talking now. Don't talk to these people, they are Billings people, you see. So, when you work with a very big source, when we give the theory and people follow it, then that's a problem. Then that's a problem. Right? So, I fully agree that the Kalman filter can do this, but Kalman filter is not a model. We'll see to that. So, nonlinear systems, we will see and we will have a coffee break. Only these three terms, the model should represent a wide class of systems. The model should be linear in parameters. Because if it is nonlinear parameters, you are in trouble. Okay. The parameters of the model should be interpretable, not like this neural network. If you can interpret a user should be able to extract, these things we will talk later, extract frequency domain information from the model, so that's it. We'll see. So unless these characteristics are there, we should not use the model, and we'll see in the next lecture how to fit the model. Gradually. Today you will do it, you will see. We'll have a break for tea breaks or something like that.
So we'll take it 5 minutes.
Yeah. So what we do 10 to 11, then 11 to 11:10 we should start from 12:10, then 12:20 to 1:20, then 1 hour. That's better. 10 minutes break is better. Yes. Yes.
नहीं उनमें सर वाइब्रेशन ज़्यादा आ रहा है
अच्छा वाइब्रेशन ज़्यादा है
हाँ
चेंज करता है चेक करता है
Yeah,
should I
yeah, you do it. Okay.
speak sir
Hello, yeah, that's fine. Hello, yes.
is this fine
Yeah, that's fine, it's fine.
एक बार इसका साउंड देखते हैं
Hello,
कमर
hello,
हाँ it is on
hello.
otherwise we have to put it here sir.
No, we checked that day, it was not coming that time.
No vibration is coming sir
With that speaker is not coming. Now it's coming. But the question is whether it will remain there or not. This point. Hello. It's coming now.
it's coming clearly but it is a problem with
Hello, and then we have to put it somewhere here. Huh?
belt or shirt
Oh dear, becomes difficult. Which one? Yeah. Yes. Now it's fine. Yeah, that's fine.
kept aside.
Is it?
Because otherwise that voice no sir will break.
Oh dear.
Otherwise we can use that method.
Is it on now?
On. It's on only. It's on.
Is on, no? It's on.
Because of your recording, that way. Otherwise no.
Yeah, I understand. So I'll keep it the phone here. Okay. Yes. Okay, I understand now. It becomes difficult. Is all right? No. If I talk like this, yes, that's fine. Yeah. So different types of models are there. As I told you that while fitting the models, always prefer to use linear in parameters models. Because if you, okay, yeah, it's coming, okay. The system must be linear in parameters. The model must be linear in parameters because not that you cannot use nonlinear in parameters, always preferable to use linear in parameters models because there is a host of least square algorithms available which can estimate the parameters, right? So we will focus on the least squares algorithm. In system identification, there are different stages. The experiment design, that is you first test whether you should fit a linear model or you fit a nonlinear model. Because there is no point in fitting a nonlinear model if the data is linear, right? Testing linearity and nonlinearity in data. Choice of input signal. We will discuss those things in detail because that is a crucial part. Choice of the sampling time. Then model structure selection, which we will not teach in this course, and that is your question. Which terms to include in the model? This is the extremely important part of the system identification. Structure selection, which terms to include in the model? It's not coming? Okay. It all right? Which terms to, this is called the structure selection problem. Then parameter estimation. Then model validation. We'll discuss all these things in detail today, right? First, you test whether the system is linear or nonlinear. If it is linear, use standard techniques of system identification. If nonlinear, then there is another problem. Whether system is chaotic or system is non-chaotic. We'll talk about chaotic system and nonlinear systems. I think not tomorrow, day after tomorrow. Okay. First to do these things. Just read it what I'm writing here. This is the important point. I'll take some time here. Given a set of input-output data, what best the model can do? A model can at best encode all information in the data, right? The question is, can the model be a true representative of the system? Depends on the quality of the data. Okay, I will give an analogy, then things will be clear. Steve always says, I remember my supervisor said, rubbish in, rubbish out. Don't put the rubbish. And if you put the rubbish, the output will be rubbish, and don't use it. I will explain these things with an analogy, things will be clear. This point is very important now. Just see. Understand this analogy very carefully, but that gives you the concept of these things, system identification. Suppose you are living in a particular town. Now you find that one particular family, new family, they moved into your neighborhood. You don't know him. You are there in the community, but you found that there is a house there and some new fellow came. Normally you see the Indian mentality, they want to see, find out everything. Who is that fellow, all these things, they have all details, right? You may not be knowing yourself, or your neighbors knew it. It's a complex issue now. Let us see, let us make the simple thing. I have got several students, let's say. So I will ask one of them. Remember, I am not telling what is my intention. I will tell him, one of my students, see, you see that particular house, there is a particular family who has moved in. Can you just go and collect some information? See the question I am asking. I told my student, PhD students, there is a person coming there, one family moved in. You just go and collect some information. Then my student asked me, why you need this information? I said, no, that is none of your botheration. I said, if I would have told you, that's a different issue. I said that, no, you don't worry, you just go and collect some information. Now the student is going to that house to collect some information. He has got a notebook, okay? He pressed the calling bell. The person came out. What is your name? Tell, my name is Mr. X. Are you new to the city? He told, yes, I just came last week. How long you will stay here? No, I got transferred, some other job. Where are you working? Oh, I am working in an IT company. Okay. Do you have any children? Yes, I have got 2 kids, 2 children, and okay, that's fine. Then you came back. Then he came back, and I asked him, who is that family? Now he told that there is a person, he transferred from Bangalore here, and he's working in an IT company, and he has got 2 children. Then I am asking him, do you have any daughter of a marriageable age? Then you say, no, I don't know. I have not asked that question. Understand very seriously now. If my intention actually is, I have got a son, I am looking for a girl. That I did not tell. Intention is not told. The objective of modeling is not known. I did not tell him. I told him, just go and collect the information. He collected the information and came here. I told, do you have any daughter of marriageable age? He said, no, sir, I did not ask that question. Then again, you go again. Then he went. Then he told, can you just tell me, I came few hours before. Do you have a daughter of marriageable age? He told us, yes, I have got a daughter. I am also looking for a boy. Then he again came back. He told, yes, Dr. Swai, they have got a daughter who is of marriageable age. Then I told, how does she looks? No, that I do not know. Go. Again go. So he can ask how, then he did not go. He told, how can I ask how his daughter looks? It is an offending question, you know. Now it is a serious problem. You understand the problem here? So how to extract the information about the system such that you can identify the actual family? How? You cannot ask all the questions. Because so what the real person, what he will do, he will go. This is exactly what we will do now. We will press the calling bell. The person will come out. Then he will tell, hey, this place is getting crowded. Why the hell you are coming from outside to Goa? You are bloody idiots. You are coming here doing not. The moment you say him that you are a bloody idiot, that fellow is excited enough. See the term, engineering term I am using. He will be excited enough to reveal all the information. He told, what the hell you are talking? You do not know me. I am this and this. I was a CEO of one company in Bangalore. I got transferred to also CEO of a new company. I have got 2 children. My daughter is the Miss India. I have got this much of bank balance and this much of stock exchange. Did this fellow ask this question? Did this fellow ask this question whether his daughter is Miss India or he is a CEO? Did he ask? He said that you are a bloody idiot, why you are crowding this place? With that question, the person is excited to tell everything, right? So therefore, while identifying the system, while collecting the data, you must apply that input which will excite the system so the system will reveal all the information. What happened? You cannot, suppose I want to know whether you know about electrical engineering or not. Suppose I want to know your knowledge about electrical engineering. You see the question I am asking. What is your name? My name is this. What your father is doing? My father is doing like this. How many brothers you have got? Brothers and sisters? We have got 2 brothers and 2 sisters. Are they married? Yes, my sisters are married and okay. When you are going to complete the degree? No, I will complete a degree next year. These are the questions. Whether he knows electrical engineering or not, how do you know it? The question does not say that. Question says that what is your name? How many brothers and sisters you have got? What is your family status? How can I know whether he knows about Ohm's law, whether he knows about semiconductor or not? Got a point? So therefore, if you rubbish in, rubbish out. You see what a point? Rubbish in. Don't ask rubbish. If you ask rubbish, rubbish will come out. And use those things to fit the model will be rubbish. It will dump in the urban sea. It has no meaning, right? So the input signal must be sufficiently exciting to reveal all the information. You apply such type of input signal. You don't apply any normal input in the system identification, right? The input signal which you should apply, that is a name, that is called persistently exciting input signal. What is that? The input signal? Input signal should be persistently exciting. What is persistently exciting? I will tell you. It should be persistently exciting. Always you to excite. Okay. Because you see, the identification algorithm, just like we can become alive if you breathe. The moment breath stops, we are dead. Similarly, the system identification algorithm will be alive if the data is coming, always, new data is coming. In the steady state, the algorithm stops. Okay. So persistently exciting every time. Okay. Suppose I am asking questions to you and irritating because you should be excited, not the normal conversation, right? Then you stop, again I will pinch. Every time you will speak. Got a point? Persistent. The effort should not stop. So the input signal must be persistently exciting. The signal which is used for linear system identification is a pseudo-random binary sequence, PRBS input, which you will do today in the tutorial. Pseudo-random binary sequence pseudo-random binary sequence, PRBS input. The theory says if you want to identify a linear system, you can apply as PRBS input, pseudo-random binary sequence. That input looks like a telegraph signal. It looks like this, you see, something like that, you see. You see, like this, a pseudo-random binary sequence signal. The PRBS signal, you should apply a PRBS signal. Don't apply a step input. Step input cannot excite. Okay. First important point. The mathematical definition is given there, doesn't matter, this is the meaning of that. The system input signal. Good question. So you understand his question first. He says a random binary sequence, why it's called pseudo-random? Okay. There is nothing like random sequence. There is nothing like random sequence. Why not? I am proving you. Whenever you are generating a random, so-called random sequence, using a finite precision machine in the computer, it becomes pseudo-random. It becomes pseudo-random because you see there is a method by which you are generating the random sequence. People must be, Professor Vida Kumar must be knowing how generating. You see, take a big number, multiply with a very high number, then there will be overflow bit. See, those type of things, how when we were students, this is how we generate the random numbers. So when you are taking a number, multiplying with a very high number, then there's the overflow bit. That bit is considered one of the sequence, one number. So accordingly, random number generated. That is a pseudo-random. That's not a random. Anything you are doing with the finite precision machine, it's not no random. Randomness is lost there. It appears to be random. It apparently random, it is not random. Right? So PRBS sequence. So remember, if the input signal is bad, output will be bad, then this identification will problem. So the signal should be such, input signal should be such, it should excite all the modes of the system. Because as I told you, we have got many characteristic modes. Okay, we are angry, we are calm, we are compassionate, we are kind, we are romantic. We have many things. We have got all these characteristics. So every mode has to be excited, right? Now the real problems comes. The system becomes nonlinear. Nonlinear systems. I'll tell you one thing. Suppose you have got a mistress. Suppose this example I always give it. You have got a mistress. You have got a wife, your children. But you have got some other formal girlfriend. Your wife knows that you are very nice. Your children know that my dad is very nice. Everything is fine. Nobody knows that you have got a mistress, hidden mode. So one day you are going in the Goa beach. What is that beach, Sonny, we went yesterday? Mirmira or something. Mira, okay. Mira is a very nice name, but Mira beach, okay. Now see here in that beach, you are going, you, your wife, your children, you understand this point. You are going and you are enjoying the beach. And suddenly you found that from the other side, your mistress is coming. The moment you see your mistress, the hidden mode got excited, you leave your wife and children and you went with your mistress. Hidden mode excitation. Got a point? It's a serious problem. Because the system has been designed, your children knows, your wife knows, your family knows that you are a gentleman. That you are a bloody idiot, that you don't know. Everything has been designed based on the assumption that you are a nice person. Now there is a hidden mode. The hidden mode got excited. Then the entire design has to change. Otherwise, system will be problematic. Got my point? So the input signal should be such. It should excite all the modes of the system. But I must tell you, the pseudo-random binary sequence cannot excite the hidden modes also. That's the problem. Hidden mode oscillations, PRBS will fail. Okay? So, but you be aware of the assumptions. Beware of the assumptions. This is a beware. You see, hidden mode, there might be some hidden mode oscillations. Clear? So, all the modes of the system are sufficiently excited. Right? Because unless it is excited, it will not reveal information. Because you are doing that information reflecting the model, right? Now, another two things I will tell you before I go to mathematics a little bit. We want to estimate the model. See what is the estimation? Oh, okay. I'll close it, okay. This is lecture 4, na? Okay. Yeah. We are sitting here. A person entered into this by this door. A person entered here, right? I am now among 20 people. I am asking you, can you tell me what is his age? This is the question. Don't measure. No measurement. You are sitting here, a person entered here, and I am asking you that you tell me what is his age. See the difference in the estimation problem now. Then she will say that his age will be 25. You will say his age will be 24. He will say his age will be around 22 or 21, something like that. Right? Now, each one will tell something because you are not measuring anything. You are not asking any questions to him. There's a person entered, I told you that you just tell me what is his age. You guess, right? You estimate. Now, which one is correct? Which one is correct? This is an estimation problem now. This is not a measurement problem. What is the problem first? It's not a measurement problem. We are not measuring anything. You are just estimating. So my statement will be like this. I will not say that his age is 25 or 24 or 23. I will not say that. See my statement, what I am telling. His age, according to her, is 25. His age, according to him, is 24. His age, according to the other gentleman, is 21. Right? So now each one of you are the different estimators. So there are different algorithms, different estimators, least square estimator, maximum likelihood estimator, total least square estimator, partition least square estimator, instrumental variable estimator, generalized least square estimator. There are many estimators, right? There are many estimators. Just like you are all, each one is an estimator, right? So I will not say which one is correct. I will not say which one is correct. I will say his age. According to this estimator, the value of the estimate of the parameter according to least square estimator is 0.5. According to maximum likelihood estimator is 0.49. According to instrumental variable estimator is this. So you have to identify that. You have to estimator, right? And the error in the estimation is called the residual error. It's not a measurement error. Understand the difference between the measurement error and the residual measure. Residual error is true value minus the estimation error, right? Now another important thing. Suppose you estimate it. We will do it in a simple one formula. Suppose you estimate. Theta is the parameter. You estimate it. How do you know whether the estimation is correct or not? How do you know? See, very important question I am asking here. There is theta is the parameter you want to estimate. Okay. So you estimate by using your method and you get theta cap. Theta cap is the estimated value of theta. How do you know what you are estimating is correct or not? Data is corrupted by noise. So theta cap is a random variable because you are estimating using some random data, right? So how do you know that your estimate is correct or not? Naturally, if it's a random variable, naturally the one method is the expected value, that is the mean value. If the expected value of theta cap is equal to theta, then it is good, right? Theta cap is a random variable, you estimate it, right? So if the expected value of that theta cap, okay, is equal to true value, then it is good estimate, yes or no? But how to check it? How to check it? Because you do not know theta. Because if you know theta, why the hell you will estimate it? You understand the problem first? You estimate it. Now you want to check whether the estimation is correct or not. The theory says the estimation is correct provided the mean value of the estimate equal to true value, right? How to check it? Because you do not know the true value. Because if you know the true value, why you are estimating it? Do you understand this problem first? It's a serious problem. Okay? How to know it? These type of problems are very common in the estimation theory. Because you do not know the true value, so we know expected value of theta cap should be equal to theta, that is good. But we cannot check it because you do not know what is theta. So there we have to prove mathematically. We have to prove mathematically that the expected value of theta cap will be equal to the theta. This should mathematically it has to be proved. You cannot know it. You got my point? So anywhere in the estimation theory, whenever you are getting these things, you have to prove by mathematically that what you are getting, that is correct. Okay. Not because you don't know what the correct value. You do not know what is you understand the problem first. Because this is how we confuse the students in the oral examination. The expected value of theta cap is theta, how do you know the theta? Right? Okay. So difference between the measurement error and the residual error is different. The residual measurement error is true value minus the measured value. Residual error is the estimated value and the true value difference, right? Estimated value different. Okay. Another problem, I am just giving the concept problem here. Given a set of input, usually the models has got max 10 to 15 parameters, usually. How many parameters? 10 parameters, let us say. 10 parameters or 15 parameters. Usually, the standard model has got maximum 10 to 15 parameters even in nonlinear systems. Okay. But you are given a set of input-output data. You will be given, say, today in the tutorial, you will find you will be given thousands data points, 1,000 data points, and you will be asked to fit a model which has got maybe 8 parameters, 10 parameters maximum. Get? Then the issue, problem. What is the problem? If the number of unknown and number of equations, they are same, you can find out the exact things, solution, yes or no? Number of equations and number of unknown, they are same, you can find out. If number of unknown is more than the number of equations, you cannot find out. This is an underdetermined system of set of equations, right? But here in the estimation theory, you are giving 1,000 data points, but you have to estimate only 10 parameters. It's overdetermined. It's an overdetermined set of equations, right? So, because it's overdetermined, the exact solution you cannot find out. You cannot determine the exact value of theta. You can estimate the value of theta. Understand my wordings here? The words I am using here. You cannot precisely determine what is the value of theta. You can estimate what is the value of theta. What I point? Two things are different. Determination and estimation is different, right? And then the question is, why you are giving more number of data points? Why you are giving more number of data points? Why you are giving more equations? First thing, we do not know how many data points are necessary, how many parameters are there to fit the system, right? And second point is, data is corrupted by noise. So by giving more number of data points, we filter it. That is inherent filtering action. So it's always better to have the more number of data points, right? Input signal should be persistently exciting. You are going to estimate it. Linear in parameter models can be represented by this form. Y is equal to theta 1 P1, theta 2 P2, theta 3 P, theta and Pn. This can be put in the regressor form like this. You say in engineering, a vector means, you are all academics, you must be knowing these things. The standard convention in engineering is, when I say vector, it is a column vector. In a standard engineering practice, just like in power system, when I say voltage, it is a line voltage. It is not phase voltage. Well, but while calculating anything, it is all, you have to convert to phase. Standard practice in power system is, when you give the data, it is a line data, but all calculations are done on phase data, right? 11 kV transmission line. 11 kV means line voltage. And you calculate the voltage. I remember, just to divert a little bit, I was appearing the interview of the Indian Engineering Service. Professor S.N. Ramchandra Rao was IISc Bangalore control professor. He was sitting there in the UPSC, in the Azan Marg or something in UPSC building. See the question. Question is, it's a very interesting question. How confusing. He told, what is the power flow in the transmission line? Sir, is V1, V2 by XS sine delta. Ah, very good. You remembered it? I said, sir, V1, V2 by XS sine delta. So what is V1 and what is V2? Sir, V1 is the sending end, V2 is the receiving end, and XS is the line reactance. Now, if the voltage is double, the power flow, what will happen to power flow? Actual power flow will be 4 times. It took a pause. The current carrying capacity of the conductor remaining same if the voltage is double, what will happen to the power? See the point. He told you the current carrying capacity of the conductors remaining fixed. If the voltage is doubled, what will happen to power flow? Somehow or other I knew it, I told the answer. You can ask your students. There this formula will not work. There the VI cosine theta formula will work. VI cosine theta is the power flow. If the current carrying capacity is remaining fixed, I is fixed, V is double, so power flow will be double, not 4 times. Interesting questions. Okay, you should know the academics, you should know some typical questions to put your students in trouble. Okay, those type of things you should know. I am telling you some questions. Anyhow, in engineering, whenever I say vector, it is a column vector. If you want to write the expressions, then you have to do the transpose or something, those things, that is up to you. Right? So this one, yk is equal to theta 1 p1, theta 2 p2, theta 2 pk. Theta 1, theta 2, theta n, they are the parameters which are unknown. P1, P2, Pn, they are known regressors. They are known. We know it. Right? So these things can be put in this matrix form, P1, P2, Pn, and theta 1, theta 2, theta n, epsilon, modeling error. So this is because row vector, so I am writing it xk transpose theta plus ek, where xk is equal to P1k, P2k, Pnk. This is the column vector, right? Because it is a row vector, so this is xk is equal to P1k, P2k, Pnk, column vector. So therefore this is a transpose. You understand this point? This one, if I write xk is equal to P1, P2 up to Pn, then this one will be x transpose. Clear? So this is the x transpose theta plus epsilon. Right? This is known, and in identification this is called the observation vector. This is called observation vector. This is called observation vector. Right? So the output, so theta is unknown, this is known, x transpose k is known, this is the error. Now if you take many number of measurements, this will be represented like this, y is equal to x theta plus zeta. If you take many number of measurements, then y will be equal to x theta plus zeta. Then this theta cap by least square error estimation is x transpose x whole inverse into x transpose y. This is the least square estimate. the theta is equal to, if you want to minimize these things, I am not giving, all these solutions are given here. You see, everything is there. So finally theta cap, the estimation is x transpose x inverse x transpose y. Right? Again I am telling here, this is not a unique value. It is not a unique value. If you change the number of data points, it will change. Okay? Because we have got over-determined set of equations, so unique value we cannot get it. So theta cap, you will get this formula, x transpose x inverse x transpose y. As I told you yesterday, any inverse operation has to be avoided. Inverse operation, division operations. So if you apply the step input, you will find this x transpose x inverse will be 0, infinity. So that becomes a problem. So step input you don't use in the system identification. Okay, you have to use the pseudonym binary sequence if the system is linear. While driving in the road, you prefer a smooth road or rough road? Smooth road, right? It is exactly the same thing in the estimation. Let us discuss few things here under 5 minutes, then we will give a break, then I will have a cup of tea. Suppose this is the estimation. This is the true value. Let us assume true value. This is the theta true. This estimate, right? Theta true is this line. This is theta cap. As the number of observations change, it changes. So the mean value of theta cap is equal to the true value, right? Mean value of theta cap is equal to true value. Okay? So it's a good estimate, right? I'm drawing another diagram. I'm drawing another diagram here. I'm drawing another diagram. This is theta true. This is theta cap. The mean value also equal to theta true, right? Yes or no? See the diagram? The mean value is also equal to the theta true. Which one you will prefer? First one or second one? Naturally, first one. Because the variations around the mean value is less. So you will say the variance is less. Variance is less. Sorry, variance is more. I'm sorry. Variance is more, variance is less. Right? Variance is more here. So, if there are multiple estimators, that estimator which gives the least variance is the most efficient. So, this one is efficient. Smooth. Variations is very less. Okay? Another example. See, this is the true value. So finally, you see, there is a difference between the true value and the actual value. So there is an error. That's called the bias error. This is the bias in the estimate. Bias means incorrect. Bias means incorrect. Right? Biased view. Biased. So bias means from the true value, how difference it is, and variance means how it changes, right? So bias, variance, we will discuss those things in the next lecture. Then we will give a break. True value? No, true value is not a variable here. I understand that. True value is a constant because our expression y is equal to theta 1 into P1k. Ah. Yes, yes. Yeah, yes, yes. No, no. Yeah, yeah, yes, yes, yes. No, no. First thing is the true value is a constant. That is the assumption. First thing is true value itself is not changing. We don't know it, but we do not know it, but we know that it is constant. Because in the expression itself, I'll tell you, yt theta 1t plus p1k t or theta 2t p2t, it is not the case. It is not theta 1t. Theta 1t means theta 1 also is varying. We assume this theta 1 is a constant but unknown. So therefore I am putting that particular line. We don't know it, but suppose there is a line theta 1. Then I am estimating it. And I am checking whether it is varying rapidly or it is not varying. So that is what the case is. This is coming under time varying parameter estimation. When the parameter itself is varying, so that's a different estimator, time varying parameter estimation. So we will give a break and for 5-10 minutes, coffee and break, then we will see. And we will see give some controversial statement. The least square criteria which you are using in signal processing, in other things, has to be dumped in the RABNC. Dump it. Least square criteria should not be used to judge the quality of a model. This may appear to be controversial, but that is true. And I will prove it why it is true. All the people in the entire universe, all the world, they are using least square error. Minimize the least square error. That's why I am telling you, just dump it in that beach, Mira beach. Don't use it. Okay? We'll see. Just close the. We'll have copy 10 minutes after that. It is not there. There? Why is not coming? Check. Hello? Yeah.
Now it's wire here. Now
Okay? Yeah. Linear parameters models. The first thing is, when you are fitting any model, let us see that if possible, the model should be linear in parameters, right? Because if it is linear in parameters, then you can use the least square technique, clear? Next point is, once you fit the model, how do you know your model is good or bad? The question is, in many places, almost all, they will say that if the model is good, if the mean square error is less, right? But what I am saying here is, mean square error should not be considered as a criteria to validate a model. Okay? That may be a guideline, but that is not a conclusion. You should not draw any conclusion from that. Why is that? I will tell you now. Before I go here, you see here. Now suppose there is a true signal. I am giving you an example. There is a signal. Actually, you don't know it. That is a sine curve, right? The data which is given to you, it is corrupted by noise, right? Suppose I corrupt this by noise, just showing it like this. This particular data is given to you. The data is corrupted by noise. This is given data. You are given this data, right? Two people I gave the data, this data. The data which is given is the noise data, right? Now they fit the model. See the model. The first person who fitted the model, his model looks like this. The output of the model looks like this. The second person who fit the model, his model looks like this. Right? See the given data, you understand? You see the given data is here, like this. Okay, data is here. Now see, if you compare it, the mean square error is less. The mean square error is more. Now can you tell me which one is a good model? The second one or first one? Second one. Because the first one not only fits to the system dynamics, but also fits to the noise present in the data, right? This is the core fitting. This model, it core fits. It core fits. Whereas this one, it captures the system physics. It captures the system physics. And the true model should capture the system physics, the system dynamics, and it should reject the disturbance, right? So if you are using the mean square error to judge the quality of the model, then you are lost, right? So mean square error under any circumstances, it can be used as a guideline. I'm not saying that you completely reject it, but it is not you should not draw any conclusion from that. You have to do many other things, right? See, this example we have given underfitting, overfitting, you see. If the data is not corrupted by noise, If the data is not corrupted by noise, then the mean square error criteria can be used. Mean square error criteria can be used to judge the quality of the model, provided the data is noise free, it is clean. If data has got some noise, the mean square error criteria should be dumped in the Pacific. Just dump it. It has no meaning. Because you do not know how much noise is there. Because you don't know that. You do not. You see, the day people will know how much noise is there, on the same day our job will go. Noise is there, our job is there. You got a point? Once you know the noise, then matter ends there. Okay? Then you deduct the noise, simple line. There is no point of doing any algorithms, image enhancement. Professor Veera Kumar is doing image enhancement. Enhance the image. Lord Sri Krishna has made the Dwarika Puri. Then that image they got, they enhance it. Okay? So noise is a good thing to keep our job, but noise is a bad thing. So mean square criteria should not be used there. Okay. How do you know it? Now suppose in this particular class, there are some idiots, outside people are there. Suppose there are some outside people are there in this particular class, okay? There are 100 people, and there are some people who are outside people. How do you know it? So I will fit a model. I will ask that you fit the model, only capture the system physics, the real people. So he will capture, his model is not perfect. Then he will reject some people. Those people whom model will not capture, I will check whether they are the bloody idiots or they are actually academics. I can check that. Residuals, I will check the property of the residual. I will ask them, do you know about smart grid? What smart grid you are talking about? Okay, then you are useless, go. Okay. Suppose, do you know about signal processing? Yes, signal processing I know. I know about Fourier. Okay, then you go there. Or by wrongly you have come here. Got my point? So the residuals should not have any dynamics. You fit the model, find the residual, check whether the residual has some dynamics. Got my point? The residual should have some dynamics. If the residual has some dynamics, the dynamics must be there in the dynamic model. So you must check the dynamics within the residuals. That is one of the best method to check whether the model is good or not. In that way you can check it. Because the data is corrupted by noise, doesn't matter. You just fit the model, find the residuals, and check the dynamics. Okay. How it is, where it's going? Hello? Yes. So model validation, one thing is sure, for you people I'm telling here, mean square error, if the system data is corrupted by noise, it should be dumped in the RMNC. Clear? Clear? Okay? Then you must have different model validation tests, right? And another thing I will tell you, modeling is an art. It has to be learned. It cannot be taught. Programming is an art. It has to be learned. It cannot be taught. What's the meaning? You can become good programmer compared to me. Okay, put it. You can become a good programmer, where I may not be. Yeah? Good. No, I think those people can fit a model and find out what sort of things are there, then you reject the residuals. So all these things, here is a practical example of some noise being generated by my talk. They should find the residuals and the programming. So you guys can do better program, right? only you can know the syntax. Syntax can be taught. So similarly modeling, I'll tell you, just a minute, I've got one doing the modeling. In the laboratory, I remember in England when I was doing PhD, and 14 people are doing. So I've got a friend from Taiwan, JJ Liu. Liu has almost finished his PhD. You see, I'm telling you, almost finished. He's just writing his thesis. Liu is not very good in analytical things. He's good in fitting nonlinear models, very good. So one of my friends is there from Singapore, G. G is now working in A-Star. A-Star is just like a DST office in India. A-Star in Singapore. G is fitting some model, some revolve flow data. Could not fit the model for last so many days. Then G was not coming to the department because he's writing thesis at home. One day I was there and Liu came. Then when Liu came, G called, hey Liu, what the hell you are doing? You are not coming to the department? You are a bloody bastard. This is the usual term. Come. He said, my model is not fitted. Then he said, I don't have time. My car I have parked. He said, 1 hour. I paid only £2. No, you come here and you see it's not getting model. It's not getting fitted. Then Liu came. You see how he's done. Like, hey, go. Okay, what is that? Oh, this thing. Just looking like this. Done. 2 months G was doing, could not do it. Liu could do it just by looking, do these things, and he's telling. So that is how I'm saying it is modeling is an art. If you know it, we are surprised. Yeah. Liu always says, he told Swai, Steve never writes excellent student to me. I told many times, Steve, you please write to our government that I am an excellent student. But I have seen he only wrote out of 14 of our PhD students, you and Eduardo. He always writes, Akshay is an excellent student and Eduardo is an excellent student. So he is very jealous of us. Hey, Swai, Steve never writes about myself as an excellent student, but I have seen your recommendation and Eduardo's recommendation. Eduardo is one of my friends, Brazil, he topped Brazilian board, and he wrote. So this is Liu. He doesn't know, analytical is not strong, but immediately you will see. And why I am saying it, modeling is an art. You can do it very quickly, anyhow. Mean square error criterion, nothing. Now see, interesting thing. Residual should be uncorrelated. You feed the model, find the residual, and see whether the residuals are noise-like behavior or not. If the residuals, if the patterns remains in the residuals, it indicates that the model has not extracted all available information, leading to biased parameter estimates. Right? Residual should be noise-like property. One of the criteria is cross-validation principle. I'm telling one thing I'm telling, system identification is a difficult subject. What I'm teaching here is a guideline, nothing is conclusive. Don't draw your conclusion from either of them. All combine and apply your brain. Cross-validation, suppose you are given 1,000 data points, keep around 700, 800 data points for your model fitting, and the rest of the things, you use it for model validation, right? That is the cross-validation principle, and the neural network people say that this is a good method. But nowadays people are saying, in your house, your mom has made very nice dishes, all good dishes. See, one of my friends, Luis Aguirre from Brazil, he told, and he wrote a paper in the International Journal of Bifurcation and Chaos. Cross-validation, you see the point. Cross-validation, you understand the meaning? You are given 1,000 data points, you feed the model using 700, and the rest 300, you use it validation. Then Louis told one day, your mom has made very beautiful dishes, dinner dishes. You will eat all the dishes, or you will say that there are all 10 dishes you have made. Okay, I will take only 5 dishes today, and the rest 5 you keep it in the fridge. What you will do, your child? You tell me. Your dishes are good. You will take, give me all the dishes, I will take it. Be common sense. And that is agreed by many people. Even David Osterk told the same thing. The cross-validation principle has to be dumped in the Arabian Sea. I am collecting 1,000 pairs of data, so let us use it for identification. Why to keep separate? You understand this point? Why to separate it out? Right? So cross-validation principle, although being used, it is not preferred by many people. Again, I am telling you, it is not conclusive. That is your judgment. Right? Cross-validation. Because that is the argument. I have got the data, why should not I use the modeling? Right? You should use it. But in your, today in the tutorial, you will given a data sets. So you will separate it in 2 parts. You will fit one part, another part. This one I will show you now. I have got an argument with one of the professors from IIT Kharagpur who has gone as a visitor to Sheffield University. He has done his PhD from Oxford. I have got an argument I remember. In the seminar, he was delivering a seminar, and the Kalman filter he was talking and doing some biomedical data. I remember there is a Sri Lankan fellow, Bisa Khan. He is the editor-in-chief of International Journal of System Science. Bisa Khan was there. One step at prediction and model predicted output. You fit a model, and he has done all his work. He has written a book also. I am not naming the name. I am not telling the name. One step ahead prediction to validate the model. Another is the model predicted output. I am writing the equations. See here. You are given a data. You fit a model. You fit a model, theta 1, yk minus 1, plus theta 2, yk minus 2, plus theta 3, uk minus 1. The one step ahead prediction is, you estimate theta 1, theta 2, and theta 3. The one step ahead prediction is equal to theta 1 cap yk minus 1 plus theta 2 cap yk minus 2 plus theta 3 cap uk minus 1. This is the one step ahead prediction. You estimate theta 1, theta 2, theta 3, and if this one is matching, you see the error is yk minus y, one step ahead prediction. This is the error. If this error is less, this model is good. Many people in speech processing, they use this one step ahead prediction. I'm just showing the example just made. Another way is the model predicted output. I'm writing the equation here. Y cap MPO, model predicted output. I'll show you now, just a minute. It's called theta 1 cap y MPO cap k minus 1 plus theta 2 cap y MPO cap k minus 2 plus theta 3 cap u k minus 1. See the difference? What is the difference? Can you just see the model predicted output is a function of its that prediction output YMPO cap k minus 1, whereas the previous one is just the output yk minus 1, yk minus 2, right? Which one is more rigorous? The second one is more rigorous. The first one is not. Right? Now see, I'm showing the example here. Just a minute. Just a minute, see here. Now, one step ahead prediction of the output. Now, I have got a system I'll show you now. I'll show you, just a minute. Just a minute. This is the system. GS is equal to this one. You identify a discrete model. The system was excited by a PR-based sequence with the amplitude plus minus 3. A total of 800 samples of input-output data were recorded with a sampling period of 1 second. The data was divided into two parts, estimation data set, cross-validation. First 400 samples are which were used for a model estimation and validation data set remaining for model testing. Now see here common sense. What is the order of the system? What is the order of the system? 3, right? Now for this system, I fitted a model. This model is fitted. How it is fitted, you can do it today. You don't refer that. This is a third order system or second order system? Second order. Why k minus 2? The lag is maximum 2. So this is second order system. K minus 1, k minus 2, u k minus 1, u k minus 2. Right? Then I compute the one-step add prediction. See, it is matching or not? One-step add prediction is this left side. Just see, it is matching. I compute the model predicted output. Matching or not matching? It's not matching. See it here? So one-step add prediction should be dumped where? RFNC. Okay, now see. Next. Then I fit I compute the step response from the model. The step response. I compute the frequency response from the model and the actual, see, not matching. But the one-step add prediction matches. Nothing, all of the things doesn't match. Now come to this point. Third order model. One-step add prediction match. Model predicted match. MPO match. Step response match. Overlapping, right? Frequency response also match. Frequency response also match. So one-step add prediction should not be used to validate the system model. Mean square error should not be used. So you must use the model predicted output. That's a better approach. Certainly a good approach. Right. How many people are working on neural network? In neural network, anybody else? Neural network. Neural network, machine learning. People say machine learning means essential neural network they talk. When the neural network came up, bit of history I'm telling you, everybody in the academic circle started working on neural network. Everybody. Because then they will publish papers. It is a nonlinear mapping. It is essentially nonlinear mapping. It destroys everything. It destroys everything. Only there's a possibility. I'll give an example first, then you will see. Suppose you employ a particular person, and whose job can be done within half an hour. That job requires in half an hour, but you employ him for 8 hours. What he will do? You tell me what he will do. You employ a particular person whose job is he can do for half an hour, the job can be finished. But you are employing him, paying him money for 8 hours. What he will do? He will do his job for half an hour, then another 7.5 hours in India, he will go and do the gossiping. He will start doing gossiping, all this bloody noise fitting to a noise. Okay, fitting to the noise. The variance is more. You understand? Variance is more. Because half an hour job is finished. Then he will go to this side, that office, that office, that office. Variance is more spread. Okay. Now suppose there is a person, his job requires 10 hours, but you ask him that you do it within 5 hours. Then 10-hour job, if he wants to do within 5 hours, naturally he is stressed, right? So he cannot go out of his seat, yes or no? So the variance is less there, right? Neural network, the problem is, it has got so many degrees of freedom, so many weights. First, the MLP, when it came, the number of layers. First layer, second layer, third layer, anything, okay? 2 layers is fine. Number of weights, okay? And what the neural network will do, 1992, MIT Press published a paper in 52 pages. You'll find 52 pages. So during that time, I was doing PhD. 94 I started, that paper was published in 1992, MIT Press. Bias variance dilemma. Bias variance dilemma is a complete case with the neural network. Neural network is very prone for the overfitting. It will fit to everything. It will fit the noise, which we don't want, because if it fits the noise, that becomes the problem. You see, once noise enters into a system, it creates a hell of a problem. You know, we are still suffering until now. This, what is that? Solar eclipse, lunar eclipse is occurring because of the 2 bloody noise, Rahu and Ketu in Indian scriptures. In the Deva, gods were there. These Rahu and Ketu are 2 demons. They sat, and when the nectar is distributed, they also took it. Now see, this noise enters there. How much problem we are still suffering on that? Every time solar eclipse, lunar eclipse occurs due to those bloody 2 idiots. Right? So you see, if noise enters into the system, that can create havoc. That can create havoc. Neural networks are very prone to fit to the noise. So therefore, they coined many words: generalization capability, bias variance dilemma, all these things came up, and I am telling you, even until now, we have not solved the problem. The bias variance dilemma problem is still there. I have got a PhD student, he completed PhD, he is now in France doing postdoc, and he joined in the Abu Dhabi as one of the academic staff. Faisal Hafiz. Faisal is a very intelligent fellow. We did all the pattern recognition techniques we used in system identification. 2-dimensional particle swarm. We developed an algorithm. Faisal has published around 18 journal papers. In his PhD, he published 12. A very intelligent fellow. He's from Gujarat. He's a Muslim fellow. Does not take non-veg food. No onions, no garlic. Faisal comes to my house, we always go for lunch and everything. Faisal told, no, Dr. Swami, I told, how is possible? He told, my maternal grandfather was a collector in one Jain community in Gujarat. So they don't take garlic and onion, so that practice is still there. Can you imagine in India? He's from Gujarat, and he never takes garlic and onion. He's one of my best students. You can see every day we talk. Still the bias variance dilemma problem is there. And it will continue to be there. It will continue to be there. Neural network, when it came up in 1990, especially MLP network, many people used it for identification, for control. The first control paper in neural network came in IEEE transaction neural network by K.S. Narendra in LA University. I have seen him in one of the American control conference in Orlando. K.S. Narendra at the Singapore conference, first paper came up. Oh dear. You can go to IEEE transaction neural network. K.S. Narendra, there is an Indian girl, student from IIT Chennai. It's a huge thing. Then Steve Billings told, was there, I was not a student, I was in India. So Steve Billings, what he did, I'm telling the history of the neural network, this system identification. He has got a student from Malaysia, Jamaluddin. Jamaluddin will always come with the traditional Muslim dress in England. I have seen it when I joined. Jamaluddin started, Steve tell, okay, Jamaluddin, this case, Narendra is doing these things. He used the orthogonal least square to fit the weights of the neural network. Do it. Jamaluddin started. Published papers in the International Journal of Control. When we went, Steve will say, Akshay, this neural network should be dumped in the Liverpool Sea. This is completely useless. He says, Steve says that neural network should be dumped. It's not used. But he has published at least 20 PhD students on neural network. The person who is telling it that it should be dumped, he has himself published around 20 PhD students on a neural network. But still, he is telling that neural network should be dumped. My friend, one Nitish Patel, he says, hey, okay, you are telling always against neural network, but your student, I have published papers in neural network, transactions in industrial informatics in some good journals. Then my friend will say, you are a bloody bastard, you are talking one thing, you are doing one thing. I told what I did. Now you are saying neural network is useless, but Chatura is publishing papers in transactions in neural network. I told him, don't ask me, you ask Chatura. See, neural network is good. It has some good practice, but you must be very careful, especially in the model validation. Don't overfit, okay? And this cross-validation, MPO, one-step prediction, residual analysis, mean square error, you should be used with cautious. Don't use it just like that. But because you have attended this GIAN course, this is my sincere request to you. You go to your institute and always tell, I will be very happy, and Professor Rahulkar and Professor Veera Kumar will be happy also, that you say, Akshay Swami from Auckland told that mean square error should be dumped in the Pacific Ocean. No, you say it. And this is the proof. This is the proof. If the data is not corrupted by noise, that's fine. If data is corrupted by noise, it's difficult. Now I show you here. So bias variance dilemma, difficult problem. Now what we did, an interesting thing, how much time is there? I will tell another interesting thing, which nobody has done in the world. We have done to, our group has done it. Discrete models, this point I'm writing, this is very important. You will also do it in the assignment, tutorial today. Today, I don't know whether today or something. Discrete model of a system is not unique. Discrete model, is it coming in the screen? Is not unique. For the same data set, you can get different discrete models with satisfying all criteria. One-step prediction, MPO, it will satisfy. It is very easy to prove because I have got a differential equation, I change the sampling time, then discrete model will change. Then how do you know? So, this is an important point. Frequency response function. Frequency response function, I will show you now on the result here, just a minute. Frequency response function is an invariant descriptor of the system. Is an invariant descriptor of the system. These things people don't do it. Entire world nobody does it. Frequency response functions is an invariant descriptor of the system. Even if the discrete models are different, if they are from the same system, the frequency response functions, if you map it, it will be same. I will show you. Interesting. Very interesting result. You see. This is the system, typical Duffing's oscillator, y double dot 2 zeta omega and y dot t omega and square y to omega and square epsilon y t q. nonlinear system. I'm not entering into nonlinear frequency response function. Identified discrete models. We identified. How we identify, I'm not telling that. We use some multi-objective algorithms. Poisson did it. Model 1, model 2, model 3. The models are different. You see the coefficient is different. Models are different. Same data set, 3 different models, we go fitted it. See the frequency response. See the frequency response. Models looks different, but the frequency response, yeah, it is the models look different, but the frequency response, see the frequency response is matching, right? The nonlinear frequency response is also matching. Okay. So that's, whether I've got other examples or I don't know. So whenever you are fitting the model, many things now, mean square error, one-step prediction, MPO, residual analysis, frequency response matching. Okay? There's so many things taken together, nothing is conclusive. And you have to apply your own brain. So from that, you can imagine how difficult this system identification problem is. It is an extremely difficult problem. It's not an easy task. Therefore, you will find in the world hardly 5-6 groups are working on system identification. The advantage being, when we are doing PhD, we do not have any rivals. We do not have any rivals because you know nobody is working on that. But if you work in the power system, you have got so many rivals. You have got so many rivals, right? Because that's the point. So you must be very careful while fitting the model. And we'll see, and this one we use it for a multi-objective algorithm. Multi-objective optimization in system identification, multi-objective algorithm in system identification was first started by Peter Fleming from our university in Sheffield. So I have got a friend, his name is Carlos Fonseca. So Carlos was married to a German girl who was doing PhD in statistics. They have got 4 children. His wife is now staying in Germany. We have to meet. I talked to Carlos few months before. Carlos is in Portugal. Carlos Fonseca was doing that job thing, first person. I do not know because Carlos will go to the coffee shop. Oh, what Carlos is doing PhD with Peter Fleming. I went to Rio de Janeiro for a conference in neural network. So there was a special session run by whom people who are working in genetic algorithms must be knowing. Kalyan Dev. Kalyan Dev was working with that, who is the genetic algorithm fellow? David Goldberg or something. Yeah, David something who found out the genetic algorithm. Kalyan Dev was doing PhD under him. So he came to IIT Kanpur, later on he is in Minnesota or something, Michigan. Kalyan Dev with one of his students, a lady fellow from South Africa. So they were presenting many objective optimization problems. Not in identification, many objective optimization problems. Faisal was there. So I told Faisal, let's go to Kalyan Dev, what is talking about many objective, let's go. And when we went, first slide, Kalyan Dev is presenting UOD conference. Photographs of Carlos. I told Carlos photograph, Carlos Fonseca, his name is. You can see the Google. He told, Kalyan Dev is telling, the first person introducing multi-objective optimization in system identification and all these things is Carlos Fonseca. So I was so proud, I thought as Carlos was doing these things, I told Faisal, the Carlos, Eduardo, we are all doing the PhD together in Sheffield University. So the question is, if you work with some big people whose statements matter and people follow it, that matters. So we can tell with full confidence that mean square error should be dumped in the Pacific Ocean. I can tell it. It's recorded, I'll tell it. We have done it, we are doing it, and we will do it. You may say that mean square error, you will use it, and you are useless. Why will you use it to prove it now? Your data is corrupted by noise, how do you know it? You are fitting to the noise or you are fitting to the data? Right? Got my point? So I'm telling modeling is an art. These are the criteria, and you should validate the model correctly. And we will see tomorrow when I start telling you the minimum variance control and subsequently adaptive control. The idea is very simple, only 2 minutes I will take it. It is the noise which creates problem. It is the noise which creates the problem. The idea by Carl Ostrom is, if noise is creating the problem, remove the noise. You estimate the noise and remove it. Simple. Idea is very simple. You estimate because you cannot know the noise. Remember, you cannot determine the noise. You can estimate the noise. See the wordings I am doing. You cannot determine the noise. You can estimate the noise. Okay? You cannot estimate the total noise. You can estimate part of the noise and omit it. We'll see next lecture tomorrow. Have a nice day.